I'm doing good, thank you.
Okay, I guess we have a few more people be coming in here. Don't expect tonight's gonna really, by no means is it gonna take up the whole 2 hours. We just need to finish up our last lecture, which means we have plenty of time. So before we finish up the last lecture, while I'm waiting for roughly the other half of the class to show up, does anybody have any questions they'd like to ask of me?
Professor, will you be posting homework number 8 solutions?
Yes, I will. I was just thinking about that. Probably give me tomorrow. I realized there was a slight different methodology to the way I solved one of the problems from the way that I taught that kind of problem. And I didn't want to confuse you guys. So let me fix it up tomorrow and I'll post it tomorrow. Good question. Anybody else?
For next week, do
Yeah.
you also have what do you call it? Office hours?
Generally, I don't. For right in front of the final, usually I'm scrambling to get the final posted and everything.
Okay.
Is the final going to be the same situation where we have to be in the Zoom call? Or,
It is the same situation where you have to get into the Zoom call to look up which final number you're taking. And then after you open up on Blackboard, after you open up your final and start taking your test, it is entirely up to you if you want to stay on the Zoom call. If you stay on the Zoom call, then you can ask me questions if things come up that are not clear. But if you don't want to stay on the Zoom call, you don't have to.
And the final for next week is Tuesday from 8:10 p.m. to 10 p.m., right?
No, it
Oh.
better not be. I can't stay up until 10 o'clock. That's
I
crazy.
think that was the final schedule on the summer semester.
I don't think so. I'll check my syllabus.
I saw that too.
What's that?
Oh yeah, I think I saw that too. The schedule.
I have it from 5 to 6:50 on Tuesday. I can look it up and see if they changed it on me. Boy, that would suck.
So which one do we follow?
Well, let me look it up. That seems really silly though, to have a class from 5 to 7 o'clock every time, right? And then do the final from 8 to 10. It seems very strange. You guys can see my screen?
Yep.
Anybody know how to quickly get to the final schedules? Yeah, I can just type it in.
This is for fall and spring. This is summer one.
Oh, I know. I'm looking for it. Here we go. Okay, so finals week for 10-week session starts on August 9th. Okay, that seems good. And at a glance dates. Okay, lecture meets on Tuesdays and Thursdays.
But that link shows fall and spring. It doesn't say summer, because that's what we had issues with our other class too.
Yeah, we had to scroll down manually.
fall and spring terms. Oh, it does, doesn't it? Spring terms. You have to scroll down manually from where?
Um,
I send you the message with the link.
Okay, summer session.
and you just scroll down, all the way down. Yeah, it should show you the schedules over there.
Okay, so that's 5 week, 5 week, 5 week, 10 week. 10 week, Monday, Wednesday, 10 week, Tuesdays and Thursdays. Class meets 5 to 7. 8 to 10 p.m.
Yep.
Can we just change it if no one's like have a conflict in that time?
Yeah, I wish. Problem is there's like 28 people in the class and there's only 17 on the phone call. Yeah, that's it right there. 10-week lectures and seminars that meet on Tuesday and Thursday. That meet 5 to 7:05 is 8 to 10 o'clock. I haven't seen 10 o'clock in 15 years. Well, okay. That's what we'll have to do. Gosh, how am I going to do that? All right. Well, anyway, figure it out. So I will send out an email to confirm because I don't want people all messed up. So we have to follow the schedule. It's going to be 8:10 to 10:10. Okay, so I think I can get into Blackboard and send out an email to everybody and I'll confirm the time. Because I know, can you send out emails? Fine. Well, I'm going to do the opposite. I'm going to send out an email saying that the final is going to be when it's scheduled according to the schedule on the board here. So we're going to do the final from 8:10 to 10:10. And I'm going to drink a lot of coffee, try to stay up till 10:10. So that'll be fun. Okay. Any other questions? Yeah. Part of it is I know at least one student isn't even in the country. So I can't just willy-nilly change things. Okay, so yeah, like I said, my syllabus says 5 to 6:50, so I'll change the syllabus and I will send out a confirming email to everybody. The final will start at 8:10 and the final will go to 10:10 on Tuesday, the 10th. I got the wrong day on there. I got the wrong class open. Okay. Anyway, does that make sense?
Yeah.
Okie dokie. What did I put here? Yeah, August 10th, I have it from 5 to 7:05, so that's got to change. Okay. Well, thank you guys for pointing that out. That's kind of surprising. Okay. So let's get out of there. Let's get out of there. Have to send an email. Okay. Any other questions before we finish up this lecture?
Professor, just to confirm, this lecture won't be covered on the exam, right?
Yeah, that's correct.
Okay.
Anybody else? Okay. Academic calendar, summer. Okay, got it. All right. So where we left off last time, let me back up a few here. Okay, so this is, I guess, far enough. So what we were doing last time was designing this retaining wall system. And what we had determined is that this retaining wall with a factor of safety of 1.5, this wall will not slide, it will not overturn. And the last thing that we checked was that the allowable bearing pressure is actually greater than the actual bearing pressure. On this check here, you notice there is no 1.5 safety factor on this one. The factor of safety is built into this allowable number that we get from the geotech. There we go. Okay, so the 3.5 KSF number that we get from the geotech, that already has factors of safety built into that number. So we don't need to clear that number by a factor of 1.5, we just need to be under that number. But for overturning moment, you have to have a factor of safety of 1.5, and for sliding, you have to have a factor of safety of 1.5. Okay, so then where we left off is in the concrete design portion. So now we're going to design the concrete wall. And because the soil is bearing directly against that wall, then we have to have 3 inches of cover minimum. So at the base of the wall was 18 inches thick at the base. The wall is only 12 inches thick at the top of the wall. But at the base is where you have your maximum moment. So we're going to look at the flexural capacity of the wall at the base of the wall with a D assumed to be 18 minus 3.5 is 14.5 inch D. The linear load is assumed to be the equivalent fluid pressure times the height times a load factor. So the load factor, according to ASCE 7 for soil pressure is 1.6. So this is what we're doing. We're calculating what this linear load is, and it's the equivalent fluid pressure, like I mentioned, times the height of where it is we're checking, times a load factor. Why do I have a load factor? Because now I'm designing concrete. When you design concrete, everything is in load factor or ultimate capacity. So I have to put a load factor on it now. So for flexure is looked at right at the base of the wall. So I have my equivalent fluid pressure of 40 pounds per cubic foot times a height of 17.5. The width of the wall I'm considering is 1 foot, load factor 1.6. That gives me 1.12 kips per lineal foot at the base of the wall. For shear, I check my shear at D up from the base of the wall. Just like the footings, just like beams, you go up D from the base. So that gives me a slightly less value by 17.5 feet minus 14.5 inches over 12 is 1.043 kips per lineal foot. So the flexural moment is the 1.12 times 17.5 over 2 times a moment arm of a third of the triangle. So that's 17.5 over 3, 57.2 kip feet. I go with my 57.2 kip feet. I use my, what should be very familiar now, my reinforcing index equation, mu over phi BD squared. Mu 57.5 times 12 over phi times the width of 12 times a D of 14.5 gives me 304 PSI. And then I can look that up in my table, and 304 PSI gives me a rho of 0.0054. 0.0054 times 14.5 times 12 gives me a required steel of 0.94 inches squared per foot. If I use number 7 bars, the area of a number 7 bar is 0.60. So my spacing requirement is my required steel divided, my steel per bar divided by my total required steel times 12. So 0.6 over 0.94 times 12 gives me a maximum spacing of 7.66 inches. So I'm going to use number 7s at 7 inches on center. My provided steel then is the opposite of this equation. I put in my per bar area times 12 over my spacing, and I'm providing 1.03 inches squared per foot of steel. Rho then is 1.03 over 12 times 14.5 is 0.0059. 0.0059 is between my minimum 0.033 and my maximum 0.181. Where did I get these values?
The row?
No, rho I just calculated. Where did 0.033 come from? And where did 0.181 come from? Okay, well, when you choose steel, I chose my steel here. When you choose steel, then what do you have to check? What are the 3 things mandatory that you always have to check?
The minimum and maximum?
There's 2. What's the 3rd? Every time you design a beam and you choose steel, what are the 3 things you always have to check before you're done? Minimum steel is 1. Maximum steel or epsilon sub t greater than 0.005, that's 2. What's the 3rd check you always have to do?
VMN greater than MU.
Thank you very much. That's exactly what I'm looking for. So how did I check the minimum steel in this case? I took a shortcut, right? I didn't do the 3 square root f prime c over fy deal, and I didn't do the 200 over fy deal. What did I do instead? Does nobody know where this number came from? 0033? Okay, hold on. All right, well, if everybody would please turn your textbook to page 598, which is Appendix A, Table A.7. The concrete we're looking at is 4,000 PSI. The steel that we're looking at is 60 grade. So according to table 8.7, the row minimum for flexure is 0033. Rho when epsilon sub t is equal to 0.005 is equal to 0.0181. Does everybody see that in their textbook, page 598?
Yep.
Okay. So that's where those two numbers came from. I did a shortcut. I didn't calculate the two equations for the minimum steel, and I didn't calculate what C is equal to, and then what is epsilon T equal to, and compared that to 0.005. I did this as a shortcut. Okay. These are things that you should be very familiar with doing a week before the final.
So, Professor, if you're in
Yes.
that range, you're meaning you're in a good design or something?
It means if 0.059 is greater than 0.033, then what that means is that the steel that you've provided, which is 1.03 inches squared, is going to be greater than the two minimum equations that we studied. One of them was 3 square root f prime c over fy. The other was 200 over fy. So that your 0.059 is greater than 0.033 is a shortcut to calculating those two equations and comparing them to 1.03. That's the minimum side. On the maximum side, 0.059 less than 0.0181 means that if you calculate epsilon sub t, right, which is equal to 0.003 times d minus c over c, then you will get a number that is bigger than 0.005.
Okay.
Okay. All right. And then the third equation, or the third check that always must be done, is phi min is greater than mu. This is a singly reinforced rectangular beam, so we are allowed to use this equation. So if I plug in my 1.03, my 60 KSI, D, 1.03, 60 KSI over 1.7 times 4 times a width of 12, I get 764.4 kip inch or 63.7 kip feet. 63.7 kip feet is greater than 57.2, so therefore I've got an acceptable design. So I cannot stress this, well, maybe you think I can, but I think I cannot stress this enough, that once you choose your steel, you're not done. You're not even close to being done. Everything that you did before this was just to help guide you to a practical solution. But just because I say use number sevens at 7 doesn't mean anything until that I've confirmed that the steel that I'm providing falls within the range of minimum and maximum, and that the steel that I am providing actually gives me more strength than is required. Only then am I done, and I can move on from my choice of number sevens at 7. And we can say the design is acceptable. Okay, now we need to check our development into the footing. This is the base of the wall. This is where that overturning moment is happening right here in the concrete. If this concrete wants to bend out and it's stressing this rebar, what keeps that rebar from just yanking out of the footing? Well, you have to have enough development into the footing. As you can see, I don't have a whole lot of straight bar development, so I'm going to have to put a hook on it, because otherwise I'm not going to make it. For a number 7 bar, I need more development length than is available in the depth of the footing. So it's really common practice in construction, when you have a situation like this, you're not going to make the footing 5 feet deep just to develop the bar. That would be silly. That would be very expensive. So you make the footing as deep as it needs to be, and then you hook the bar to get that development. But we still need to double check that even with the hook, we meet the requirement for LDH. LDH is the greatest of the following. This is from our development lecture. And so I need to calculate A. A is equal to 60,000, and my size, I didn't go through them this time. It's uncoated rebar, the size effect, and the other one was top bar. It's not a top bar. Over 50 times 1 times square root F times C. And I need 11.6 inches, or I need 8 times the diameter of the bar, which is 7 inches, or I need 6 inches. So of these 3, the 11.6 will control. And 11.6 is much less than 27 inches, the depth of my footing, so we're okay. Okay, any questions about this, about the flexural design of the wall?
I have a question on that hook.
Yeah.
Can you go back to the figure? It's
There.
like, what's stopping me that the hook is going to the left? Can you design it going to the right as well?
Yeah, that you pointed to the left is kind of just standard detailing practice. And the reason why we do that, the code doesn't make you do that. The reason why we choose to do that many times. Why is this not? There we go. Is this is in tension. So that means this is in compression. And with this being in compression, it's going to form a compressive strut that goes back to the hook there. And so we just feel better as engineers that it hooks towards the compression strut, not that it hooks away from the compression strut. If it hooked away from the compression strut, there's nothing in the code that says it's not going to work. But it's just kind of intuitive that it's not going to work as good, because now the compression strut has to go over like that. So that's the only reason.
Oh, okay. Because I thought it was at the moment to like how it rotates.
No, because all the hook does is just develops the bar, and the bar is in pure tension right there at the point of maximum moment.
Right. Okay. Okay. Thank you.
Sure. Any other questions on the flexural part? Okay. Okay, so the shear design. We're still looking at the wall, but we need to make sure that the wall has adequate shear design along with adequate flexural design. So the maximum load for shear design we found to be 1.043 kips per lineal foot. The shear demand is 1.043 times the height of the wall above that D point. Shear is always looked at D above the end of, or bottom of the wall. So it's not the full 17.5 feet that we use for flexure. It's 17.5 feet minus D, gets you to 16.29 feet. So the shear demand is 8.5 kips. Our capacity is 2 lambda square root F prime C BWD. So this is hard rock concrete. So 2 times 1 square root 4,000. Width of 12, D is 14.5. I get a capacity of 22 kips. That's my nominal capacity. My allowable capacity is VVC is 16.5 kips, which is greater than 8.5 kips. So we're okay. Retaining walls, like footings, don't use shear ties. It'd be very, very impractical. In fact, let me go back to the diagram. It's not impossible, but just impractical that you're going to go in here and put a whole bunch of ties in this direction. They would have to go like this. And why are ties impractical? Because this wall may be a couple 100 feet long. So you'd have to place hundreds of these things side by side to provide a leg that is perpendicular to the wall, 1 or 2 legs every feet. So that would be hundreds and hundreds of ties. Again, you could do it, it's just not seen because it's somewhat impractical. If your shear demand didn't work, then usually what you do is just make the wall thicker, not add steel in that direction. Okay, so we get down here. Okay, so shear capacity is greater than my demand. We're okay there. Now we look at horizontal steel. Horizontal steel is controlled by ACI 318, section 1161, table 1161. So for bars greater than a number 5, they are looking for a row factor of 0.0025. So the area steel required with 0.0025 times B times D is 0.435 inches squared. So with the number 6 bar, my provided area steel is 0.44. So if I do my equation where I put my bar over my required, I got 0.44 over 0.435, which is just over 12 inches. So I can use number 6s at 12 inches on center for that wall steel. And so the number 7s at 7 are vertical bars. They're for the bending of the wall, so the wall has sufficient out-of-plane bending, and they're placed towards the back to give you the most leverage against that bending action. The number 6s at 12 are horizontal bars. I know in this image you really can't see them, but there's little dots. Let me draw one of them, just kind of clarify. They're on here, but they're really small. So they're dots that look like this, and that represents horizontal bars. So they're running in and out of the page horizontally, forming basically a grid with the vertical bars. And they're there to provide crack control and some out-of-plane flexural resistance. Basically, they're a minimum required by the code, but they most certainly strengthen that wall and give it structural integrity. So the horizontals are number 6s at 12, and the verticals are number 7s at 7. The design of the footing at the toe as well as at the heel follows the design process for footings as described in lecture 15. That was our last lecture. And that is it. Anybody have any questions for retaining walls?
So that number 7 bars is whatever the length of the wall it goes into the page of it, right? Is the
Let me bring it back up. Okay, so the number 7,
oh, I mean number 12.
The
Number
number-
6.
okay,
Yeah.
number 6 is the length of the wall. Yes. If that wall is 40 feet long, you can use 40-foot long pieces of number 6 bar. If that wall is 200 feet long, then you would splice them. So you probably bring in 40 or 60-foot pieces of number 6 bar, and you would splice them at the ends, overlap them per our lecture when we talked about rebar development and lap splicing. You would just lap splice them. You could, I suppose, mechanically splice them, or you could weld them as a splice, but nobody would do that when it's far, far cheaper to just overlap them by a foot or two and develop them.
Okay, and then just for clarification, the soil is in the right side, and then the yeah, it makes sense. If it's in the left side, your rebar will be on the left side as well.
Correct.
Okay.
But just because you mentioned it, I'll bring up the original. Going through a few hundred slides here. There we are. Why does that not want to work? Okay, we'll do it this way. Now that takes forever. That is so bizarre. Okay, there we go. So that's the original geometry of the problem. And yeah, if the soil was on this side, then the wall, you just mirror image the whole thing. So the wall would be shifted over to this side because you want more of your footing to be under the soil than out here, right? So the toe should be fairly close to the wall. The heel should be further away from the wall, because if this thing's going to try to rotate and lift up, you want it to have to lift up as much soil as practical, because all this soil back here, although it is the soil that's trying to push the wall over, it's also that very same soil that's holding the wall down. So that's a common geometry that you see on the screen. Any other questions for me on retaining walls? Okay, well, what do we have? Like an hour and 20 minutes? Who's got questions you like to ask? This is your last chance before the final at 8:10 on Tuesday.
The exam is cumulative, correct?
Yes, sir.
Okay.
And you're gonna email us about the time, right? Just to clarify.
As a confirmer, yes, I will.
Okay.
Yeah, I'll probably put that together tomorrow with the corrections to the homework number 8 solutions. I'll put those two together. But yeah, we'll do it from 8:10 to 10:10.
Hello?
You talking to me or to somebody else?
Oh, no, sorry. I was just making sure you could hear me. But I just wanted to ask, since you won't be having any office hours until the exam, I guess, anymore, is it okay if I email you this weekend if I have any questions?
Oh, of
regarding-
course.
Okay, perfect.
Oh,
Thanks.
yeah, of course. Over the weekend, I mean, give me a little time to respond because I won't have my computer open and all that. But yeah, absolutely. Any other questions for me? All right. Well, hopefully this was not as painful as it could have been, and hopefully you learned something this semester. I do appreciate how you guys have stuck it out. I know that one, concrete is a lot of material. I do understand that. And I still remember taking concrete. And when I was undergrad back in 92, 93, I took the concrete class, and it was just your head spinning because it's so much information. But after a while, it kind of sinks in and makes sense. So thank you for sticking through this course that has a lot of information. Thank you for sticking through this course that is accelerated. We did this in 10 weeks instead of 16. And thank you for putting up with Zoom. It's kind of, that really was the icing on the cake, I think, was to try to do all this disconnected. But hopefully we did the best we could. Hopefully you walk away from this a positive experience and that you've learned some things. And if there are no further questions for the final at this time, you can, as Valerie said, you can always send me an email and I'll respond to as best I can if you have any questions while you're studying. And with that, thank you much for all your attendance and participation, and good luck on the final.
Professor, do you
Yes.
teach other design class?
Not at the moment. I have. Over the last 16, 17 years, I've taught all kinds of different things, but it seems lately where they really, really need me is in the mechanics of materials. So I just keep doing that over and over. And then I do the summer thing for fun, because I'm a concrete guy. So they just throw me a bone for the summer. But that could change at any time.
But so you also teach steel and timber?
I have. It's actually, I've never taught timber. That's probably the material I am absolutely the weakest on. Don't ask me to design your house. I wouldn't have a clue. Haven't had a timber class since, well, I had to learn it again to study for the ASC, but since then I've forgotten everything I know about wood. I taught steel, but that was a long time ago. So mostly concrete, structural theory, mechanics, statics, stuff like that.
Retaining walls?
Just in this one, yeah.
Oh, okay. I
Yeah.
was looking at the design classes. And I'm taking retaining walls this semester and steel and timber.
Do they actually have a class on retaining walls?
Yeah,
Oh, no kidding. Oh,
4,400, I think.
oh, nice. Okay. Yeah, no, that was never offered for me. That's kind of why I threw it in here as the last lecture, because I went through this whole system, undergrad and masters, and never had a single lecture on retaining walls. So that's why I threw it in here. So yeah, that's good to know. Okay, guys, thank you very much. We'll see you on Tuesday.
Thank you, Professor.
Thank
Thank
you.
you.
Professor.
Thank you, Professor.
Thank you.